Hi, welcome to another edition of BC Theory. Hopefully the lighting for the video camera is a little better now. Changed some things in my apartment. All right, so we're going to continue with our series on discrete math, and we are going to be talking about something called propositions and logic. Namely, we're going to talk about propositions, and the big segment we're going to start is logic. So the idea behind this is that we want to form statements that are either true or false. And we want to relate various concepts together such that if something is true, then something else might be true. So we want to form some kind of implications about various different concepts. And that's what propositions allow us to do. So in propositions and logic in general, we're going to be talking about Boolean variables. So in the sense that Boolean variables are going to be either true or false. Okay, so each variable is either true or false, but we're not going to actually start with variables. We're going to introduce them at a later point. Today we're going to talk about propositions that don't have variables. So here these are no variables, at least for the moment. We will later. So what is this? A proposition without variables is either true or it's false. It either is true or it is false. So let's write that down. So either true, and we're going to denote that with T, or false, and we're going to denote that with F. So just as a simple example, a true statement would be, at least now, the statement, it is the, if I can spell, it is the year 2020. If you're watching this in the future, then obviously it's not 2020, but right now it's the year 2020. So this statement is a proposition because it is true. There's no, like some cases where it isn't true, and some cases where it isn't true unless you're on another planet, and if you're on another planet, get into contact with me. All right, but there are some false statements that I could make, such as, at least now, I am the Queen of England. I mean, it's very likely that that'll never be true for me, but at least now it is not true. So that is a false statement. So we can have true propositions statements or false statements, okay? So the thing is, well, okay, we can just deal with a bunch of statements, but that's not really that interesting. What we want to talk about is when we combine propositions. So let's try to combine propositions. Because in some cases, well, maybe we have something that some statement that we're looking at and some other statement, or maybe we may have some statement or a different statement. So we want to see, well, what happens if we have a combination of these propositions? So the way that we're going to do this is we're going to say we're going to let P and Q be propositions, any ones that you want. Okay, so now we're going to talk about how do we combine these two propositions. Well, P could be this proposition, Q could be this one, or they could be any proposition that you want. So we're going to define various things. So the first one is going to be P and Q. So the symbol in the middle is something that's called a wedge, and that means and. So the way that you should read this is P and Q. Okay, so we're writing this in a formal way so that we can write propositions in a formal way. We could talk about what it means when we have two propositions with a and in between. We could write the word and, but we want to write this in a formal way. And this is the way we're going to do it. So this is saying that we have one gigantic proposition with two smaller propositions, P and Q, and we're forming the and of them. And what is this defined to be? So this is true if and only if P is true and Q is true, and is F otherwise. So, I should lower that. So we're saying here that the only way that this proposition can be true is if P is true and Q is also true. And that makes sense, right? If you have something and something else and you want it to be true, both of the two halves have to be true. So then you may be thinking, okay, well, we can just do a similar thing with or instead of and. So one proposition or another proposition. So P or Q. And the way that we're going to write this is with a V. This is called a V in between because it looks like a V. I don't know why this isn't called upside down V, but this one's called V. So the way you should read this as you may expect, P or Q. And you might expect that this is true. Oops. So this proposition right here is true if either P is true or Q is true. If both of them are true, great. If one of them is true, great. If neither is true, then the whole thing is false. And that makes sense, because if P is false and Q is false, then P or Q should be false. So the way I'm going to write this is false if and only if P is false and Q is false. Okay, so if it's not the case that P is false and Q is false, meaning one of them is true, then this is true. So then I should say is true otherwise. Oops, there. Okay, so those are some basic operations that we will consider. So the more popular way to actually write this instead of doing it this way is with something called a truth table. And what it does is it gives you an outline of what the result will be of the expression that you're considering. So let's just take P and Q as an example. So how do we actually make, oops, not A, P and Q, how do we actually make the truth table for this? So what we do is we're going to make 3 different columns of a little table right here. So the top is just going to be the labels of the columns, and I'm going to call them P, Q, P, and Q. Oops, not A, P, and Q. And we're going to have, in this case, 4 rows after that. And what they're going to correspond to are the 4 possibilities of what P and Q could be. So P could be true. Actually, I'm going to do this in a different color so it's easier to see. Let's do blue. So let's set P to be true in this case and Q to also be true in this case. Or it might be that P is true and Q is false. Or the other way around. P is false and Q is true. Or both of them are false. And what we're going to put in this column over here is we're going to put the result of what is occurring in that row. So for this entry right here, the top one, we're going to put whatever true and true is, which we know is true. So T is going to go here. For this entry, it's going to be the result of T and F, which is false. And in fact, all the other entries are false. Because the result will be false if and only if at least one of the 2 values is F. And we can actually do something similar for or. So I'm going to copy this over to here, make it a little smaller. And I'm going to interchange this for or. And again, we still have the same 4 rows right here because there, again, are still 4 possibilities. And so what are we going to put over here? Well, let's eliminate the possibilities and then think about what will go there. Well, oh, I should fix this. So this should be P or Q. So then what are we going to actually put here? Well, what is true or true? That's going to be true. And in fact, the first 3 are going to be true because P or Q is going to be true if at least one of the 2 is true. And in this last one, they're both false, and that is defined to be F. Okay, so that is another way we can actually formally encode this proposition. And now what we can do is we can build bigger and bigger propositions, and we can make a truth table for the result. And so suppose that we have n variables, then there are going to be n different columns for those n variables. So in this case, we have 2, but in general, we may have n. And in that case, we're going to have 2 to the n possibilities because each of the propositions could be true or false independently of all the other propositions because they're arbitrary propositions. Okay, so let's do another one. So the next one is actually really important, at least in some of the things that I do, is something called implication. And that's going to be written P arrow Q. So the way that you should read this is P implies Q, that Q is true. So what does this actually indicate? So the best way I can describe what this means is let's just do a truth table because that's a formal way of describing what happens. So again, I'm going to have PQ, P arrow Q up here. And then let's have our 4 rows again. And let's do this in a different color. Let's do orange. So true, 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 false, false, true, false, false. So what is this truth table going to be? It's going to be true here, false in this one, and true in the other ones. So the only case where it's false is when P is true and F is false. So you can actually see that this is not symmetric. So if I look at P implies Q and Q implies P, those are not the same thing. Because if they were the same thing, then these 2 entries would be the same, but they're not. So that implies, no pun intended, that this this proposition is not symmetric with respect to the ordering of P and Q. It matters which one is on the left side of the arrow and what is on the right side of the arrow. So what is the intuition behind this? So suppose that P on the left is true. Then that means that this thing that is true, this statement that's true, is implying Q, which is the proposition on the right side. Well, if P is true, then there's no real implication that's occurring. So once it's true, then the only thing that matters about the whole proposition is whether Q is true or not. So that's why in the case of where P is true, the result is the exact same thing as what Q's value actually is. So then what about these down here? What if F is false? So, and we see that the P implies Q is automatically true. So regardless of the value of Q, the result of the whole proposition is true regardless of Q's value. So why does this occur? So in these 2 cases right here, we have something that is called a vacuous statement. And for a bunch of reasons we may get into at some point, there's a reason. It's a good idea to set the result of a vacuous statement to be true. So let's just do an example of one. So if I'm the Queen of England, then I live in the United States. I just made that up as an example. So if we look at this right here, the beginning part right here, that is the thing that's implying the second half of the proposition, which is the part in blue here. So the part in red is the P statement, and the thing in blue is the Q proposition. So the red statement, from what we have talked about earlier, is false. And so therefore this whole proposition is going to evaluate to true regardless of what the second half is, even though it's true, at least now. The whole thing is going to be true immediately. Okay, so that's just something to remember here, that when you have a the first part of the implication is false, then the whole thing is true. But if the first part is true, then what matters is whether the second one is true or not. So let's do an example of that one. So I should say that this evaluates to true. And so let's do another one. So let's actually flip this condition around. So if I live in the United States, then I'm the Queen of England. Okay, so I'm actually flipping around the P and the Q proposition here. I'm just flipping them around. So I'm gonna just underline. So the red part again is going to be P, the P. The P statement, and the blue part is the Q statement proposition. So we know that this part right here, at least now, not false, it's true. I currently live in the United States. And the part right here, this currently evaluates to false. So according to our table right here, we're in this second row right here. So this whole proposition right here evaluates to false. Okay, so this is actually an example right here of why you can't just flip around the two conditions and get the exact same result. Okay, so that actually gets us to some new types of implication. So let's actually look at this. So the types of implication. So the original, so to speak, is P implies Q. But we can also have Q implies P, have it the other way, and this is something called the converse. Okay, so in this example right here that we just did, this is the converse of the one up here. So this actually tells us that if we have a statement, if we have a statement and we form the contrapositive of, the converse of it, then it's not necessarily the same. So if we have a converse of a statement, it's not necessarily equivalent to the original. If there's no implication whatsoever, then there's no converse to start with. But it may be the case that the converse is equivalent, but in this case it might not, just so you're aware. But sometimes we have a bidirectional operator. So P arrow back and forth Q. So another way of saying this is if and only if. So another way to actually think about this is true if P and Q have the same value. and false otherwise. So in some sense, for this one, if it's true, then that P and Q are equivalent to each other. They're both true or they're both false. Okay? And you can actually figure that out. This is actually the same thing as saying, maybe I shouldn't write that way. So this is the same thing as P implies Q and Q implies P. And you can actually verify that for yourself with the truth table. Put it in the comments. Okay, so another term for this is a bidirectional implication. But we usually just say if and only if. So whenever you see if and only if in some statement somewhere, it means that P implies Q and Q implies P. Okay? So that is actually something to consider. But probably the most important, well, that one is very important. But a very, very, very important one is something called the contrapositive. So this is the implication not Q implies not P. And what are these? These right here are the negation. So whatever Q's value is, it's the exact opposite when I put the negation symbol on there. Okay? So this is called the contrapositive. So I want to actually do the truth table of this because it actually tells us something really important. So let's actually do this. And what I'm going to do here is I'm going to make the table even bigger because I'm going to put more columns in it, and you'll see why. So we're going to have our usual P and Q columns, just like before. And what I'm going to do here is I'm going to have not P right here. And then I'm going to have not Q right here. And then I'm going to have not Q implies not P, which is what the contrapositive is. Okay, so then I'm going to have my 4 rows, just like before. Make them big enough. All right, so here we're going to have our true, 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 false. So this is unchanged right here. Okay. So then now in this column, I'm just going to evaluate what not P is. So it's the exact opposite of what the P column is. So in the first 2 entries, I'm going to have false. And in the second 2, I'm going to have true. Okay, so it's just the opposite of what the P column is. And then the Q column is going to be exactly the same idea. False, true, false, true. Okay, so then now what we're going to do is let's evaluate what this is. So in this first one, this says that not Q, this guy right here, implies not P, this first one right here. Well, remember that in an implication, if the left side is false, the whole thing is true. So we're going to have true here regardless. And in fact, this third entry is also going to be true as a result. Okay. So then now let's see, well, what is this entry going to be? Well, the left side of the implication is true. So the only thing that matters then is what is on the right side of the implication, which in this case is false. So then we're going to put false here. And in this one down here, we're going to put true on the right side, again, because not Q, the thing on the left side, is true. So therefore, this one's going to be true. So notice something interesting here. This is actually exactly the same thing. So this is equivalent to the original statement. Even though, so it's exactly the same. The truth value is identical, unchanged. And that's actually quite surprising because Q was on the right side of the implication. Now it's on the left side. And we saw before that the converse was not exactly the same, where you flip the order of the two, but by putting these negating symbols at the front, that changes the fact that it's not the same to being exactly the same. And that's actually quite surprising to actually see. But the thing is that so you may think, okay, so what? Who cares that we have these statements? The thing is that they're extremely important in proving things. So here's an example. And if you're watching the theory series, we do this sort of thing with something called the pumping lemma all the time. And if you know what that is, put down in the comments. So suppose that I want to prove that some implication is true. I want to prove that some implication is true. But in some cases, it might be hard proving this. So it may be hard or unreasonable to prove this when I assume that P is true. That just might be really hard to do. But suppose that using Q is a lot easier. Well, this one is a lot easier because Q is on the left side. And so if I can prove this one right here, I can prove the original one because they're equivalent to each other. So if I can use this one instead of this one, then fine, because it's equivalent to the original. And quite an awful lot of the time, this is a lot easier to work with because the P statement is often really hard to assume or try to find examples of, but when the Q statement is false, by finding a counterexample to Q being true, that's a lot easier to find sometimes. And then trying to imply that P is false or whatever, that's a lot easier. So that's just something to keep in mind. Okay, so those are some basic operators. We talked about propositions, and then we started to combine various propositions with and, or, and then most importantly, implication. In one proposition implying another. So I hope that was interesting. Put interesting propositions down into the comments down below. As always, please like and subscribe to the channel. It really helps us out. And as always, I'll see you next time.